In order to solve trig equations, you first need to solve, which means I want to isolate my trig function if I only have one trig function in the original equation. If I have a squared or something else, you may need to factor instead, but get it equal to 0 before you factor. And then you could also try using an identity before you factor. So use one of these methods to solve, and then once you have sine equals, cosine equals, tangent equals, whatever, then you have to take it one step further and to find two angles for each of your thetas, and we're going to use the unit circle. I have an asterisk there because there's a caveat. It's not always two angles. If sine, cosine, secant, or cosecant is 1 or -1, then there's only one angle. And if sine and cosine are not between -1 and 1, if there's a 2, a 3, a million, a -5 million, then there are no angles. Both of these will occur in example 2 during this video. Before we do some examples, let me refresh your memory. The identities that we're going to use are the Pythagorean identities and the double angle identities. And this time, you're going to need to know these other two versions of the double angle identity for cosine. All right, let's do an example so I can actually show you what I mean. All right, this is our first problem. There's multiple cosines in here, so I can't just isolate my cosine like I did last time. And before I even try and figure out how to factor this, notice that this cosine has a 2 theta with it, and this one has a theta. You can't do that. You can't mix angles. Those are two completely different angles, and you cannot mix them. So instead, let me rewrite this one using the double angle identity in terms of just thetas. Okay, we have 3 options for how we want to rewrite my cosine 2 theta. You only want to use one of these options because I don't want to mix sines and cosines in here. I just want to deal with, let's use this last option because we already have cosines in the rest of my problem, so let's just keep cosines in this problem. So I'm going to rewrite that cosine 2 theta as 2 cosine squared theta minus 1. I still have that minus cosine theta, and I still have that plus 1 equals 0. All right, combine like terms, which means I have 2 constant whole numbers here that I can add to 0, add together. They happen to add to 0 by pure accident. And now this is my problem. Okay, I have to solve this by factoring because we're still on this first step. We replaced using an identity, and now we need to factor. And so reminder, if you have 2 terms and you're factoring, you want to pull out the greatest common factor, the greatest number or term that they have in common that you can pull or divide out front. If you have 3 terms, you want to use bottoms up method. So in this case, I have 2 terms. Notice they both have a cosine theta in them. This one's cosine squared, so that is the same thing as saying cosine theta times cosine theta. If you need to rewrite it, do that. So I can pull one of those cosine thetas out front, and I'm left with a 2, a cosine theta, and everything pulled out here, but use 1 as a placeholder. Remember, when we factor, that's how you do. If everything pulls out, you use 1 as a placeholder. Okay, so now it's factored. All right, good. Let's set each factor equal to 0, and I'm going to find 2 angles on the unit circle where cosine equals 0, and 2 angles on the unit circle where cosine equals 1/2. So once you factor, you set each factor equal to 0, and it's just like we have 2 problems that we are isolating to solve. So find 2 angles here, and find 2 angles for your 1/2. All right, cosine theta is your x coordinate piece on the unit circle. So cosine theta equals 0 at pi over 2 and 3 pi over 2. And then I also need to find 2 angles for where cosine is positive 1/2. That occurs here and here at pi over 3 and 5 pi over 3. All 4 of these angles are part of my final answer. All right, let's do another example. This time I'm going to use a different identity, but it will follow the same steps. I'm going to have to replace with an identity, factor, and then find 2 angles for each factor. All right, for example 2, I'm mixing cosine squareds with a sine. It's not a 2 beta anymore. It's squared. So that's your hint that I am going to replace this piece with the Pythagorean identity. Remember this guy? But I don't just have cosine squared here. I have sine squared plus cosine squared. So remember, you're going to have to rearrange this. If I subtract my sine squared over to the other side, I rearranged this identity and I got that cosine squared is 1 minus sine squared. So I can replace this with 1 minus sine squared. Now I can get this equal to 0 and factor it because I have a sine squared and a sine. I don't like having negative squared terms, so I'm going to add these pieces over to the other side or subtract them over to the other side. And I like to write from the squared terms first. Here's my only sine piece. And then these two constant whole numbers I can add together. I combined like terms and reordered it all in once. Okay, now that it's equal to 0, factor this. You can use bottoms up, or in this case, it's a little bit easier than that. There's no number in front of my sine squared. So I'm just going to have to think to myself, what two numbers multiply to 2 and add to 3? Well, that would be 2 times 1 and 2 plus 1. All right, so now that I have it factored, you want to set each factor equal to 0 and isolate your sign. And then same idea here, set it equal to 0 and isolate your sign. And now find 2 angles for this one and 2 angles for this one for your overall answer. Okay, you may have already realized that there is no sine fraction on your unit circle that's equal to 2. Or remember, sine and cosine will never be a number that is not between negative 1 and 1. Sine and cosine are always between negative 1 and 1. They're always fractions between negative 1 and 1, or including negative 1 and 1. So 2 is not between negative 1 and 1, which means that I'm going to have none for this one. And then use your unit circle. Where is sine equal to negative 1? Where's my y-coordinate negative 1? That only happens here. So this one is a double whammy example. It's showing you both of your caveats here. I ended up with one where I had no solution and one where I had only one angle instead of the usual 2 and 2. But it's still solved the same exact method. They're just those two specific cases. Let's do 3 more examples. Okay, we're gonna continue with Pythagorean identity, but let's use one of the other versions, just so you're really prepared and you have an example of everything. I have a tangent squared and I have a secant. So because I have a squared here, this is your hint. You want to replace the squared term, and I want to replace it with something that I hope has secant in it. So use your identities here, the Pythagorean identities, and notice tan squared has a secant in it. So if I rearrange this identity, if I subtract my 1 to the other side, I can rewrite tan squared in terms of secant squared. And now move everything to one side of the equal sign. You have to have it equal to 0 before you factor. I'm going to also rearrange it because I like to have it in squared term first and my constant whole number last. All right, I replaced with my identity. I have it equal to 0, so now I am ready to factor. And this one, I can, again, there's no number in front of my secant. So again, I'm going to say, okay, what 2 numbers multiply to 2 and add to 3? It's the same 2 numbers that we used before. Set each factor equal to 0. and now solve. Because these are secants, I'm going to use reciprocals, so I'm going to put these over 1. The reciprocal of secant is cosine, so if secant is -2, cosine is -1/2. And if secant is -1, cosine is also -1, because you just flip your fraction and 1 over 1 is still 1 over 1. So unlike last time where we got no solution in one answer, this time because it was secant instead of sine, I am going to have answers here. So where's cosine equal to -1/2? Where's my x coordinate point -1/2? That's at 2 pi over 3 and 4 pi over 3. And where is cosine, the x coordinate piece, equal to -1? That only happens here. So if cosine or sine is with -1 or +1, there's only one angle there instead of 2. And that's it. Let's do 2 more examples just to make you feel comfortable with this. So in this next example, I have a theta mixed with a 2 theta. So that's your hint. You're going to have to replace this with your double angle identity. And luckily, this time I only have one option. So I have 2 sine theta minus, replace all of this with 2 sine theta cosine theta. And now that I've replaced it, I need to factor it. Get it equal to 0 and factor. This one's already equal to 0 for once, which is helpful. Factor it. It's only got 2 terms, so you just pull out what they have in common. So they both have a 2 and they both have a sine theta. If I pull that out, everything cancels out here, so use 1 as a placeholder, and I'm left with just my cosine term here. And I can set each factor equal to 0. 0, if I divide my 2 over, it's still 0. And if I subtract my 1 over and then divide by -1, cosine equals 1. So I'm going to get 2 angles for this. Where's sine theta equal to 0? Where's my y coordinate point 0? It's here and here. Use 0 and pi. Don't use 2 pi here. Use 0. 0 and pi. And where is cosine equal to 1? There's only one answer there. If sine is 1 or cosine is 1, there's only one answer, and that occurs at 0 again, which we already have listed, so we don't have to list it twice. All right, last example. Let's do a double angle again, but let's do cosine because you have multiple options here, and I just want you to feel comfortable with that. So I'm going to replace my 2 theta, because I have a theta, an x, and a 2x. So I need to replace my 2x using the double angle identity. And for cosine, we have 2 options here. Since the rest of the problem has a sine in it, I want to use this middle one here, the one that also has a sine. All right, now that I've replaced my identity, you want to get it equal to 0. Check, it's already done. And now factor it. So I'm going to rearrange it because I like to have my squared terms first. Oh, I don't know why I mixed thetas in here. I was following along with what the identity was. But these should be x's since the original problem used x's instead of thetas. And then I hate having negatives here. It is okay. You can still do bottoms up with a negative, but I'm going to change all of my signs. You're essentially multiplying everything by -1, which changes every sign, and it changes the sign of 0, but 0 doesn't have a sign, so that's why it works out that way. All right, I'm going to use bottoms up method to factor this. You should know how to do that by now, but you can factor using whatever method you want, and you can even use quadratic formula if you prefer that. All right, if you factored, then you should have gotten this answer. Set each one of these factors equal to 0, and you will get these answers. If you use the quadratic formula, it will go straight to this piece. So you don't have to do that extra set it equal to 0 and solve. Quadratic formula will automatically give you these 2 answers, whereas if you factor, you have to then set them equal to 0 to get those answers. All right, now find 2 angles for your first sine and find 2 angles for your second sine. Where is sine, the y-coordinate piece, equal to -1? That only occurs one time at 3 pi over 2. And where is sine, the y-coordinate piece, equal to +1/2? Your two angles there are pi over 6 and 5 pi over 6. Include all three of these answers in your final answer. And I haven't mentioned this before, and I should have. If you want to double check your answer, you can type this into your calculator. Make sure you're in radian mode because we are in radians. We have pi's here. And you would type in pi over 6 and pi over 6 and make sure it equals 0. You would type 5 pi over 6 and 5 pi over 6 and make sure it equals 0, and 3 pi over 2 and 3 pi over 2 and make sure it equals 0. So you'd actually type in negative sine 5 pi over 6 plus cosine 2 times 5 pi over 6, enter, and make sure it equals 0.